Welcome, ladies and gentlemen. This is MN37, Properties of Trapezoids in Kites, sections 8.5 and 8.6 in your textbook. We have a great big trapezoid on your note guide to start with. I'm going to label the vertices A, B, C, and D. And if I asked you what you know about trapezoids, I hope you would say from previous math courses that you know that the bases are parallel, really, and that is, except that it's a four-sided figure, that is really the only interesting thing about a trapezoid. So let me kind of take a step back again. I just want to, I don't know if you caught my words. This is a base, and I know you would probably say that's the base, but this is also considered a base, and those bases are parallel in this trapezoid. So over here, I'm going to say AB is parallel to side BC. And you know what? Compared to all those other shapes we've been dealing with, this is it. That's it. That's all the properties there are for a trapezoid that you're probably thankful for that after those parallelograms and rhombuses, squares, and rectangles. But let me give you a little more information just about like the language of trapezoids. We would call this a leg of a trapezoid, and we'd also call this a leg of a trapezoid. So if you see a four-sided figure with only one parallel side, that means you have a trapezoid. There is this thing called the mid-segment theorem. I'm right here in your note guide. And really, we've talked about mid-segments in the congruent triangle chapter, which I think is chapter 4. I could be wrong, it could be 5. But anyway, what the mid-segment is of course we have a midpoint over here. And if this is a midpoint, well, first of all, we'll name it E. That means that this length is equal to this length. And over here in BC, we have another midpoint. Ooh, I can do better than that. Hold on a second. It's right here. And we'll call that F. And that means this length is equal to this length. And the mid-segment is literally when you connect those 2 points. So this right here is the mid-segment. And there is kind of what you're looking when you're looking at it. There's 2 parts of this mid-segment theorem that's interesting. One is that you have the mid-segment that will be parallel to your bases. So what we're saying is that AB is going to be parallel to your mid-segment, which is EF, which is also parallel to DC. So that's one interesting thing about the mid-segment theorem. The second is about the lengths. I'm going to switch colors here for a moment. I'm going to say if the base here is 9 inches and the base up here is 5 inches, and if I asked you what do you think the mid-segment length is, it is the average. So you take your 9 plus your 5, divide it by 2, which is going to give you, in this case, 7. And that is precisely the length of your mid-segment. So when you average your bases, the length of your mid-segment is that length. So I'm going to bring it down here and make sure that you have it in notation form. So we have the measure of EF, which is your mid-segment, so this is your mid-segment, is going to equal the length of BC not BC. I was looking at that, I'm like, oh, not BC. AB plus BC divided by 2. Okay, and that's where we got the 9 plus the 5. Actually, I suppose to be more technical, the AB is 5 plus the 9 divided by 2, and that's going to give you that 7. So that is really all there is to typical trapezoids. Now, of course, we have to have something special, right? And we do have a special trapezoid. It's called the isosceles trapezoid. And notice again, it is a trapezoid, it has four sides, and you have one set of parallel sides. And again, before we get going, how about I label these A, B, C, D. And if you look at this trapezoid, it's a little different than the top one simply because you'll notice that this length, AD, is congruent to this length over here, which is BC. So you do have, kind of like an isosceles triangle, you have two equal sides or congruent sides. Same thing with an isosceles trapezoid. Now, let me just kind of write a couple things here. First of all, we know that AB is parallel to DC just simply because it is a trapezoid. We know because it's a special trapezoid, isosceles trapezoid, we know that AD is also congruent to BC. And here, because you have the isosceles component, this base angle at angle D, this base angle at angle C will be congruent. Again, very similar. I'm going to draw an isosceles triangle up here. Isosceles triangle means that this side is equal to that side, and the base angles, of course, also equal. Um, and we talked a lot about the reasoning for that, and that applies here as well. So angle A then, of course, is going to equal angle B. So let me throw those up here. So we have angle D is congruent to angle C, and angle A is congruent to angle B. And one of the very, very important, oh, and I almost forgot, angle A plus angle D is going to equal 180 degrees by default, because here's what's happening. You have base angles the same, and so angle A, and we know that a quadrilateral has 360 degrees in it, so angle A and D will add up to 180, just like angle B plus angle C will add up to 180 degrees. We haven't talked about diagonals, and really the typical trapezoid doesn't have anything interesting with the diagonals, but the isosceles does. If I draw in my diagonals in green here, the interesting thing about the diagonals, and I'll write it down here, and this only applies for the isosceles trapezoid, is that the length of AC, which is the one diagonal, is going to be congruent. So the length of those diagonals will be the same. And that's really important to remember. Okay, so the isosceles trapezoid, a little special case of the regular trapezoid. A lot of different little properties that might be intuitive, but something definitely you need to remember. Coming down here, we have one more shape in the quadrilateral family, and then you know what? We're done. We don't have any more after this. It is a kite. And just like it looks, it does in fact look like a kite here flying to the right. I'm going to label it as A, B, C, and D. And if I asked you what you know about a kite, I would hope that you would say that AB, just by even looking at the picture, AB is congruent to AD, and that is in fact true. So this length is in fact equal to that length. Also, BC is congruent to CD. And again, you probably intuitively could have figured that out. There is something interesting about the angles. I will tell you that angle A does not, and I can't stress it enough, does not equal angle C. That is not the case. Remember this. This is a number one mistake that I see. Actually, look at this. I'll even do this. So angle A does not equal angle C, but angle B does or is congruent to angle D. So this angle right here does equal this angle over here. And think about a kite and the symmetry of it. So that does make sense that obviously angle A, B, and D should equal. Now, the most important thing about a kite will be the information about the diagonals. So let me just write diagonals down here. And I'm going to draw the diagonals. How about I do it in green again? So here's my one. Oops. Ooh, I can definitely do that over again. Okay, here's... Oh, that wasn't any better. Sorry, you guys. I'm gonna try here. You know what happens? I'm shadowing myself. Okay. And here's the other diagonal. Okay, so first of all, look to see if the diagonals are congruent. You look at them and clearly they're not the same length, so that's not an issue. But what you can see, hopefully, is that kind of like the crossbars of a kite, we've got a 90-degree angle right here. Um, and we're going to call this point, by the way, E in here. So what we have is that BD is going to be perpendicular to AC. And that is very, 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 very important because then you have right triangles. Right triangles means that you're going to use Pythagorean theorem or your SOHCAHTOA to solve different things. I will also say this, that BE, oops, not BC. How many errors have I made today? Oh, BE is going to be congruent, and I'll put it up here. BE is congruent to, yes, you are right, ED. Okay. So again, we've got a fair number of different properties here. Many of them are intuitive. The big one that you cannot assume is that angle A is congruent to angle C, but the ones that might not be as intuitive, but you need to remember are those diagonals. Diagonals are the easy ones to forget. Now, if you flip this over, you'll notice that we have a great big quadrilateral family. And I'm going to be doing most of this in class, but what you need to do right now is to actually write down your family tree. So quadrilaterals is the big head family name, and keep in mind I'm going to be filling in all sorts of information within the family tree, so don't make the name too big. So leave yourself enough space that you can draw a little diagram and also talk about the properties. So that's kind of why I made the big boxes so large. So the quadrilateral family, then we have the parallelogram family over here. That so they're still quadrilaterals, but they are going offshoot of the parallelograms. This is trapezoid over here, and this is all by its lonesome, the kite family. They chose not to produce any more shapes, I guess. Notice the trapezoid family is kind of short and sweet. The only thing we have here is an isosceles trapezoid. And here we have, as a subcategory of the parallelogram family, a rectangle and the rhombus. And of course, both of them got together and created the golden child, which is the square. Okay, so each one of these we're going to be talking or creating a summary so you can really see what properties each one has. Actually, what's the definition of it? What are the important properties and which families they belong to kind of keep you organized here as we finish this chapter. So we will finish this table up in class as a class discussion tomorrow. Thanks for tuning in.